started, I'm hoping that other people will come in. The first part of the presentation is more just about like what Wireshark is, where the current status is, what's going on with it, and stuff like that. And let's get started. If you have any questions, just send me an email, aa@cisco.com. There's obviously a very good Wireshark support alias that's on there. I've got references to it near the end of the presentation. So what is Wireshark? So Wireshark is a free open source network protocol analyzer. I'm not going to call it a network sniffer. Apparently that's a trademark name, so I'm going to stay away from that. It is multi-platform. It runs on Windows, Linux, Solaris, the Mac, which is sort of implied, NetBSD, FreeBSD, and a number of other platforms. There's a CLI as well as a graphical display. There's hundreds of protocols supported. There are more being added every week. So if you just sit on the development alias, you'll see like a new support thing come in pretty much every week. Even though it is free, there are people that work on it, that spend lots of time on it. It was originally created by Gerald Combs. While he was a master's student, he was a creator. He's the lead developer since 1998. There's lots of other people that work on it. Guy Harris, a person from MIT. He's one of the maintainers. Gilbert Ramirez. He's actually a Cisco employee who moved over to India. He works on the Windows implementation. He builds it, sends it out, and stuff like that. There are many contributors, and there's an author list. I myself am on there. There's lots of I'm sure there's people in this room that have contributed to it. There's the libpcap folks. If you're familiar with the BSD implementations of libpcap, Richard Stevens goes through a lot of stuff in his book on it, on his seminal book. Then there's the WinPCAP folks, which have taken the libpcap code and made it work on the Windows platform. And recently, with Wireshark, with the Wireshark renaming from Ethereal, there's a company that's been formed. And I'm probably going to not say it right, so I'll just spell it CACE Technologies, which basically is funding a lot of some of the development for WinPCAP, Wireshark, a lot of some other stuff. Okay, they do trainings and stuff like that. I'm not in any way associated with them, just a Cisco person. So how is Wireshark used today? Like I said, I was in the TAC. We use it in troubleshooting all the time. Performance issues, it really helps out over there. As you know, the PCAP format encodes the timestamps of when the packets were taken, and you can do deltas in between where the packets are coming and going. People use it for security analysis, see what ports are open, which ports are going on, what other ports a particular session is using. I use it for learning about a protocol. Like when new things get added into BGP, sometimes it's better you have the RFC on one side and you have the debug trace on the other side, and you look at what actually the implementation is doing. Many times what the RFC is saying is not what the implementation is doing, even if it's written by the authors. So these things have been known to happen. Protocol development. So I know the NetFlow developer. I'm actually one of the TMEs for NetFlow, and we use it every day for NetFlow development. And in fact, when you come up with new fields and stuff like that, we verify that it's decoding it properly. Okay. The Wireshark website looks like this. You can get the source tarball, you can get the SVN repository. It used to be CVS. SVN is, let's say it's just a new name for CVS. I'll go more into that. There's multi-platform compiled sources there. There's documentation there. I'm going to answer the question, which is probably going to come up later, is why is it called Wireshark and not Ethereal anymore? The reason is that Gerald Combs, when he left the company that he was formerly with, and I don't know the name of the company, it apparently had the rights to the Ethereal name and the website. So rather than trying to fight with the company, he just renamed the program, which is a GPL source. Okay. The other thing I found really interesting is I've started up a Wireshark wiki, and there's lots of protocol references over there. If you go look up like the other day I was looking at for some stuff on gratuitous ARP, because I think Vista has a bug in it or something like that. I won't say that too loud with our Redmond folks here. But it has a pretty good description of how gratuitous ARP works. It even has a packet trace of what it should be looking like and what fields should be filled in and how they should be filled in. There's a growing sample PCAP library. If you guys have PCAPs that you can share, please add it to that website. Taking out any security things that you have in there. I'm sure you guys are already familiar with this. This is what the GUI looks like. We'll actually be working in the middle pane, this pane over here, if you can see the pointer. Yeah, you can. So we'll be adding stuff that'll get populated over there. I have an example that we'll be going through. Okay. As you know, you can acquire packets. You can choose There's a little display that shows up that shows you like how many packets you've captured, what type they are. I really wish they had CDP over there, because a lot of times I'm trying to figure out, I'm sitting on the host, which host am I connected to, which switch port I'm connected to, and CDP really helps over there. So I don't know how long I have to wait to get the CDP packet, but yeah. Okay, then there's capture options. The only thing I would add, I think you guys are probably familiar with this, what's kind of nice is that you can have rotating buffers, in which case if you don't really know how much, really don't know how much traffic you're going to be capturing, you can capture to multiple places, and it can keep on rotating through them. And you can have another file that goes through and checks the logs and the PCAP file and everything. Okay. One thing to keep in mind about Ethereal and Wireshark and stuff like that is generally these tools run with root. So to put the port into promiscuous mode, you have to be super user and you have to run as super user. So there have been security issues with Wireshark code in the past. And generally, I mean, you have to realize that there are lots of people putting in code into Wireshark every single week. So it's not surprising to have breakage here and there. So one recommendation is to use another program, TCP dump, which also is capable of generating a PCAP file, to do the actual capture, and then you do the analysis in Ethereal or Wireshark. Or the other option is to use T-Shark, and only use it for the actual capturing, right? Which puts it at the same line as where TCP dump is today. Okay. In terms of getting the captures, this is probably the only time I'm going to be talking about Cisco, so don't bash me for like being vendor. I did put in Junis, so it should be clear there. So there are lots of ways of getting the PCAP files or getting the capture data. So if you have a switch, there's features like span, rspan, which lets you go to a remote router, and you can switch to a local analyzer port, and you have a PC hanging off of there. Vendors have IP packet copy features. So there's an ER span, which basically encapsulates the captured packet into a GRE, and you can send it anywhere you want. And generally, what people have done is they'll create like a loopback on a Linux box and advertise that the reachability for that prefix, and they'll capture it on that box. There's iOS IP traffic export, which does the same thing on an iOS box. The additional feature with that is you can actually create the PCAP file locally on your flash, or if you have like the newer boxes have USB keys you can stick in, you can save it on there as well. Junis has port mirroring, very similar to the span feature. I believe you can do sampling and filtering at the same time. Flexible NetFlow. If you aren't familiar with flexible NetFlow, it has the capability to basically export the payload of the packet, of the entire payload of the packet to the NetFlow collector. Okay, and I think there was alluded to earlier this week about that you can use the lawful intercept features that are in our hardware if you can figure out how to use them, and if you know how to use SNMPv3. That's how you get to it. There's embedded capture. There's a 6500. You can do a monitor type capture. There's other like platforms out there that basically run TA3 on them. So one example that we have is there's a WAS-WAY module that we sell, that Cisco sells, that has this stuff. You basically run like the free software on there, and it captures the PCAP file for you. So a lot of platforms have that. Then there's also specialized hardwares that vendors sell. So in the Cisco example for that is NAM modules that you can stick inside a 6500 or an ISR. There's NetQS, I believe, does the same type of, I'm sorry, NetScout probably does the same type of stuff as well. Okay, so there are some current limitations with the PCAP file format. One is that there's only a single link type per file. So if you look at this case, if you look at the IP packet copy feature, right, a router can have ATM interfaces, it can have Ethernet interfaces, it can have frame relay interfaces hanging off of it. When you're capturing on multiple interfaces, let's say you're copying on a particular destination address or source address, how do you represent that in a PCAP file? So today that's not possible. There are other things that they're running into limitations of PCAP, like what if you want to do annotations within the PCAP file? Like if you're doing some sort of analysis, you want to share your analysis with other people, you want to do commenting on a particular frame or a particular section of the packet. There isn't really a way to do that today. There is a solution that's going to be available in the next version of Wireshark, 0.996. It's called the PPI, the Per Packet Information Header. So if you're familiar with MPLS type technologies, or 802.1q, they're basically adding in a new shim in the PCAP format. So this shim will allow you to basically add in new TLVs, and you can put in whatever type of information you want. Okay. So once you've got your frames, you can do all sorts of analysis on it. in this example, I'm doing a filter, a display filter for CDPs. It shows you all the CDP frames that were captured. In this one, it's showing you the session, the back and forth of some of the stuff. And there's some export analysis. There's some commercial programs that do this a whole lot better, but this is the cheap man's export analysis. It tells you that there's some duplicate acts, there's some keep alive acts. It gives you like a basically lay of the land of what's going on with your TCP sessions or with other sessions as well. There's some histogram type stuff on packet length, as well as, so this is one of the more interesting things. I used this recently with, I was doing NetFlow performance analysis on routers, like how fast can a router, how many records per second can it export? So keep in mind that's not the same as packets per second, because there could be multiple records inside of a packet. So using using an expression, you can actually make Wireshark count the number of NetFlow records that are inside of a particular packet and do a histogram analysis on it, and you can come up with a chart very much like this that says at this particular time, this was how many records per second were being exported from the packet. Just by having the PCAP file there for you. All right. Let's get to the stuff that we really want to talk about. So first I'm going to go through like some basic architectural stuff, like how does the actual dissection work, which is what they call decoding. Decoding is known as dissection in the Wireshark world. And then we'll go through an actual example. Okay. Wireshark limitations, the way it works is there's only really one file open at one time that you're analyzing. If you want to open another file, open up a new Wireshark. Each packet basically has a frame data structure, and it's basically, think of it as a dual linked list, where one frame data structure points to the next packet's data structure, to the next packet's frame data structure. And this data structure basically has information about the packet, such as the time of capture, the size of the packet, and most importantly, where to get the data. Like where is the location of the actual data for that frame in the file. Okay. Once protocol dissection starts, it starts basically when you select on the top pane the actual packet, and it will go through and it will basically decode the entire packet up until the end. So there will be a link layer dissector, which is generally going to be Ethernet in our cases. The Ethernet layer will call the IP, and then IP will call TCP, and then TCP will call BGP, and then BGP will have its own little dissection schemes for the different types of message types that are in there. Okay, it keeps on chaining until there's no more. There's a dissector that doesn't really call anybody else. Okay, the dissectors register as startup. They create a parent-child relationship with other protocols in dissector. So it's basically when you start up Wireshark, you'll see like a little graph going up, and that's when the different dissectors and plugins are basically registering into this parent-child relationship. Okay, in terms of dissection, this is where the magic happens. So if you bear with me, don't fall asleep. The tree pane, which is this thing over here, where you see the type IP, which is an Ethernet frame, so it's type IP 0x800. That is being generated by a typed function, and most of the things in Wireshark are actually typed functions. So if you are familiar with how network protocols work, almost everything, a lot of things these days are basically TLVs, or you have some sort of field, a fixed field that has particular, like a value will map to some sort of meaning, right? So in the case of the IP ether type field, 0x800 means IP, right? So this is what this is doing. It's saying this ETH type, that's the name of the header format. The name is called type, which maps to this type name showing up over here. Then there's an abbreviation, eth.type. This maps to the search capability in Wireshark. So when you're trying to do a search on pretty much anything, this is the nomenclature you would use. So you'll say eth.type equals 0x800, and it'll pop out all the IP packets on the Ethernet. Okay. Then field type, unsigned integer 16. This basically means it's 2 bytes. So whatever the size of that thing is, it's 2 bytes long, right? That's how much data it's going to go grab once you tell it where in the packet to go get. When you display it, you're going to display it as hex, which is where this 0x800 thing is coming from. You can display it as a bit field, which would be the 001, 11, whatever, or you can display it as hex or as a decimal. So the vals, ETH-type vals, this basically points to a table, which I have below over here, which has the mappings. So ether type _IP is a constant set to 0x800, and that is IP. The IPv6 one is a defined underneath, and this went on for like several hundred lines, so I didn't copy. I was nice to you guys. If there was a bit mask that you needed to like flush this against, this field against, then you would put it in where the bit mask is set. So right now 0x0, which means you're going to get whatever you put in, right? There's no masking going on. And the blurb is something just descriptive about what this field is. You can put cookies and milk, whatever. It doesn't really matter. In fact, most of them are actually left blank. This one in the code was actually left blank. I just put in ether type just to be nice. So it makes sense. Okay. So this was how you define the actual fields. Okay. Now you need to map these fields into the actual lay of the packet. Like how does this field map to an actual packet? And these are done by a bunch of functions that are in the format proto something do something. So generally it's going to be proto tree add item, and you can refer to one of the HQ fields, and I have an example. I have an example further on does that. Or you could actually completely ignore the HF fields that we defined earlier and just come up with your own string, and just say you can just put in whatever you want in there, and have an example of that as well. Okay. Basically, what it does is it basically attaches a new tree to an existing tree. So you basically have to find. So in this case, this ether type thing was attaching to the end of the Ethernet packet at that point in time. Right? And I'll show you how that works when we work through the example. Okay? The most important thing in here is the start. What is the offset from the packet that this field that you're interested in, where does it start, and then what is its length? So offset and then length. And that is how much it's going to grab. And if you look at this section over here, you'll notice that offset and length is what gets highlighted. So when you select something on the pane, it's nice enough to actually highlight that stuff in the hex window at the bottom as well. So you can figure out, a lot of times that's where a lot of the problems are, is like you'll notice what it actually thinks something is not what it's actually mapping to, which is where a lot of the bugs come from. Okay. Any questions so far before? All right, cool. Next section. Why would you want to add to Wireshark or Ethereal or to any basically protocol analyzer? I mean, what's the point of this? So I did a search on Google, and I don't remember what I was searching for, but I found this nice quote. Some Dean Wilson, and I don't know if he's a famous person or not. So, but there's a guy called Dean Wilson, and this is what he said. The switch talking to the master radio did have a lot of blinking lights, but watching blinking lights to measure traffic is about as accurate as using your tongue on a battery tester. So on a 6500, there is something akin to this. They have a bunch of LEDs that go up and down based on the load. So you could be figuring out like how loaded your fabric is based just on that. It doesn't really help you in trying to figure out where the problem is or who's doing the DOS attack or what. But that is one method. But why would you want to add to Wireshark? I mean, it really helps you out in the end. And if you look at the actual changes that go through on Wireshark, there actually aren't that many actual new protocols themselves. They're basically additions to existing protocols. So every month there will be something added to BGP. There'll be something added to LDP. There'll be something added to OSPF or something like that. It's just like maybe 10 lines of code. That's all it is. And if you know where to make the changes, it's an extremely simple job. And it beats looking at blinking lights, by the way. So, okay, the first thing you need to do is basically get a build environment. You can use Windows as an environment, but I found that it's extremely difficult to set up. Not that many people know how to use it. And I think the Windows people basically hang out in some other forum and not on the Wireshark aliases or in any of the forums where I hang out. So if you know of a better way, or if you have an environment to get that, let me know, and I'll post it somewhere. You could use Sigwin under Windows. Apparently that does work very well. It doesn't use the native Windows rendering format. You have to run the X server that comes with Sigwin. Okay. Unix, Linux, including Mac OS environments, very easier. For Mac OS, you can actually pull down the FINC sources and you can compile it right from there. In terms of getting the source, SVN is the best. You can also get the tarball. The SVN thing is, the reason why I say it's the best is the SVN, the Wireshark maintainers actually do a very good job of making sure that Wireshark at any point in time is always buildable. So not just anybody can go in and commit code. They actually run some tests even before they commit just regular patches, not just like the release time type stuff do they start getting worried about this type of stuff. So I used to actually maintain at one point the Wireshark Ethereal implementation for the engineering community within Cisco. And I don't think I've ever actually downloaded the tarball to build that. I'll always just check out like a CVS checkout and just build from that on a weekly basis until it just became like something happened with our Solaris environment where it just stopped working, but that's another story. Doing the checkout, SVN, CO, and then you just give a URL and the directory that you want to check it out in. What this does is it's very similar to CVS. It'll create a Wireshark directory for you. Checkout is from the latest code. It's from what they call the trunk. Okay? It'll create an entire directory structure. This is what the directory structure sort of looks like. The interesting point is in terms of what we're trying to do, which is basically add to protocols, is there's a directory called EPAN, and underneath EPAN there's a directory called dissectors. And that's where all the dissectors live. Okay? In terms of building, I do have a VMware-based Linux environment that if you want to copy, you're free to copy. It's all ready to go. It has all the build tools for Wireshark. In fact, it has 2 Wireshark checkouts, and it has the code for what we're going through. So I have it up here. If anybody wants it, grab it. I would have put it up on some website, but it's 3 gigs. So unless somebody wants to host it for me, and I don't want to use BitTorrent, otherwise my ISPs will cut me off. Okay. After you do the checkout, the next thing you want to do is basically there's a script called autogen.sh. This basically further sets up your environment. It'll create the configure script for you. If you do the tarball, if you download the tarball, it will already be the autogen will have already been run on it. In some cases, that might be the better thing to do. In our environment at Cisco, what I've found is even autogen doesn't work very well. So sometimes I'll copy down the tarball and I'll use that. Sometimes that won't work either. But that's a problem specifically at Cisco with our Solaris environment. Okay. After you get done with the autogen, the next thing you need to do is basically run configure. And that'll go through and it'll find whatever it needs to find, and it'll generate, most importantly, is a makefile. Once configure runs and it runs without errors, the next thing you want to do is type in the make command in the Wireshark directory, and that'll probably take like 20, 30 minutes. It'll compile Wireshark for you, and after you do that, type in Wireshark, and something like this should pop up. So once you get to this point, you're pretty much ready to go in terms of adding the new protocol into your environment. Okay? And you know that it's not something that you added that messed up Wireshark. It worked out of the box. Some words of caution: if you are fairly familiar with C programming, keep in mind that Wireshark is a multi-platform program. There are some limitations on what you can do and what you're not allowed to do, because there's some platforms that don't work properly if you do certain types of things. It's not C++, so don't do any comments with // no zero-length arrays, no inlines. There's a whole list of them. There's a readme.developer inside the docs directory that has a lot of this stuff, and it's a fairly long list. Me, myself, what I do is I just look at what other people have done and I just do copy and paste. So I'm actually pretty good in that I won't be breaking any rules that way. Okay, so the sample exercise we're going to be doing is adding BGP MDT support. So what MDT stands for is multicast distribution tree. It's an addition to MPLS VPNs that allows multicast VPNs to be built over the core. What the MDT specifically does is it carries the source. How MVPN works is it basically creates a multicast GRE tunnel from one PE to the other receiver PEs. And what BGP MDT does, it advertises the source and the group that VPN is going to be using. The source being inside the P router and inside the P cloud, as well as the multicast group that's going to be used. Okay. There's an IETF draft. I think it's expired at this point, where all this is documented. So currently Wireshark, at least to this day, still doesn't support MDT SAFI. They're still waiting for my chain set to be committed. So if you're quick enough, you can get a SVN checkout and you can try this out yourself. So the way we're going to go about this is we're going to first go ahead and identify the work items, like what needs to be done, and then actually go out and implement each one of them and test each one of them individually to arrive at the final solution. The PCAP file that's being used is at this website. And in addition, if you just replace the file name with mdt.diff, D-I-F-F, that'll have actually the finalized chain set that we came up with. Okay, identify work items. So if you look at the BGP trace, what it looks like is the MDT actually advertises the new multi-protocol reachability NLRI, and it's a new one. It's 66, SAFI 66, and you'll see that, excuse me, Wireshark is actually saying that it doesn't know what it is. So that's one thing that isn't working properly. You should know what 66 is. The second thing that's broken is that the next hop address isn't broken down into what it actually is. If you look at it down here in the hex, it is there. Just the display doesn't like spell it out for you. So that's the second thing. And the final thing is the actual NLRI itself isn't broken down into the actual components. So it isn't telling you what the MDT source address is, what the MDT default address is, or what the RD is, the route distinguisher is. Okay? Okay, so the things that we need to do is fix MVP and SAFI as unknown. We need to fix the next hop address so it's expanded into an IPv4 address, and we need to fix the NLRI information inside the update so it's actually understood, rather than saying unknown SAFI. So obviously all three items are related to BGP. This basically means that you're constrained to two files inside the dissectors directory, packet-bgp.c and packet-bgp.h. So you'll find that if you're working in one specific protocol, it's only going to be two files at max you're going to be touching. And it's generally going to be, and the dissectors are basically in this format. There's packet-some sort of protocol, and then C or H. Okay? So first problem, the MVP and SAFI is unknown. So the way the Wireshark code is basically written is that they'll have, like in bgp.c, they'll have like a list of the value to text mappings up near the top. And remember we went through the HF fields, how they have, you know, this ether type maps to IP, this thing maps to IP. These are generally at the top of the file. And interestingly enough, I open up the file and it's like the 20th line down. You have the different SAFI to unicast. So SAFI, SAFNUM multicast means multicast. So it has all the listing over there. The problem is I don't know where these constants are defined. The SAFNUM, unicast, and all that stuff. So I just did a grep for that, and I found that SAFNUM unicast is actually defined in packet-bgp.h. Good enough. So I added my new guy in there. I called it SAFNUM_MDT, and I gave it the number 66. I referenced the draft that was in, and then I went back to the original packet-bgp.c, and I added in the SAFNUM MDT that I just created, and the text, which is the multicast distribution tree. Right? Easy enough. I recompiled, just run make again, and it works. So it was just basically just 2 lines of code for doing that. Okay. Notice that you didn't really have to do much with like the C code. It was basically just filling in a table, and that's pretty much it. Most of the changes are going to be like that, by the way. So next hop, the second problem. The next hop address isn't expanded into the IPv4 components. It just shows you the length, which is 4 bytes. We already know that. It's an IPv4 address. It's slightly more complicated in the last example. What we'll do is, again, I'll open up the packet-bgp file. I'll do a search for that text, the next hop address, next hop network address, and lo and behold, there it is. I can see where it's putting in the 4 bytes, so next hop length, byte, 4 byte. So what I need to show up after that is some sort of pull-down tree that actually has the breakdown of what the actual IP address is. Okay, so note over here that there's a new tree being added, proto item add subtree, and that subtree is called 3. And if you go on, what that subtree is being added to, the text for that, is coming from this function, this MP address to string. Okay, if you look inside that function, it basically has a list. It has a case statement, a switch statement that says if it's unicast, if it's multicast, if it's uni-multicast, if it's a tunnel, and the length is 4, you print it out. You print out that it's a IPv4 packet, and you decode it as an IPv4 packet. So all that needed to be added in that case was that I just needed to add my SAFNUM MDT that we already defined in the first section to that switch statement in here. And that was it. See? So it was easy enough as that. Okay. The third one is actually the most complicated one. This is what the actual breakdown of that NLRI looks like. So there's 8 bytes of a route distinguisher. There's the MDT source address, which is an IPv4 address. It's the BGP. It's usually the BGP next hop. It doesn't have to be. And then there's the MDT group address, which is the multicast address that the GRE tunnel is going to be destined towards. Okay. If you look at, in the case that we actually highlight NLRI, you'll notice that it would have highlighted the hex code at the bottom. And if you decode the hex code, this is what it looks like. I mean, it has the RD in there. It's 904:82. This is on a test network, so it doesn't really actually mean anything. Don't try to map this to like one of your competitors. So it has a source address and it has a multicast destination, and you'll note that it'll repeat to the next NLRI one after another. Okay. So looking through, this is like the fourth function inside the BGP file, and you'll notice that if you look at any of the other decodes, that the NLRI is actually decoded using this function, decode prefix MP. The way it starts off is that it starts off decoding for IPv4 unicast, multicast, and labeled prefixes. So what we need to do is basically add in a section for our new SAFI that we created, the SAFNUM MDT. And this is what the actual change set is. And I'll break this down into separate components, and I'll go through each one of them. So we created the case statement SAFNUM MDT. The next thing we need to do is basically the way the NLRIs are created inside BGP is each NLRI has a length statement that tells how long that NLRI is. That's useful when you're doing like IPv4, when you're advertising IPv4 routes that can have variable prefix lengths, because you're advertising the mask at that same point. In our case, it's not really useful. So what actually happens in the actual encoding is it's always going to be 128 bits, right? Because we're advertising an IPv4 address, we're advertising an IPv4 multicast address, and we're advertising the route distinguisher, all of which are constant length. So it's always going to be 128 bits, 16 bytes. Anything else is basically a malformed NLRI. So what this code is basically doing over here, it grabs the first byte, which is supposed to be the length in NLRI. So that's part of multi-protocol BGP. It has nothing to do with MDT SAFI so far. We check the length of that, and if it's not 128 bits, we basically print out an error message onto the tree saying there's something wrong with this NLRI. It isn't supposed to be here. Okay. The next section, what we do is we look at the RD, and we move the offset counter by 1. So that's what we're doing over here. We move offset equals offset plus 1. And this is where the RD is supposed to start. And remember, the RD is 8 bytes. So what we do is we basically, there's a function over there called RD to string, and that basically converts the RD into the variety of RD formats that are there. So this is one of the problems with RD, is that if you're familiar with route targets and route distinguishers in BGP, is that they can have a variety of different formats. So there's the colon format where you have number, colon, another number, and there's the IPv4 format where you have an IP address and then colon and then a number. What this function does is basically just creates a string from either of those different types of formats. It sort of hides that complexity from you. Okay, so you basically give the offset over to that function, and what it'll do is it'll give us back the fixed string inside this variable RD underscore string. And then what happens next is we move forward 8 bytes, and that's where the IPv4 source is, and we grab that. So TVB is the buffer, offset plus 8 bytes. We grab at that, we get the IPv4 address. So these are TVB get IPv4 is actually a function from Wireshark that basically is good for getting IPv4 addresses. The other nice thing it does is it actually quantifies that it is an IPv4 address, and if you do DNS type stuff, it'll decode it into like an actual host address and stuff like that for you. We store those two values. We store that value in IPv4 address.address, and then we grab the next one, which is the multicast address. So you go ahead 4 more bytes, so offset plus 12. Okay, grab that guy, stick it in there. The next thing we have the 3 pieces of information. We have the RD, we have the IPv4 source, and we have the IPv4 destination multicast. After that, we just need to attach it to a tree for display purposes. Okay. In this case, it's just going to be a free line of text showing the RD, and I have an example over here. So what it eventually looks like is it says RD equals some string, comma, next hop equals the source IP address, and then comma default MDT equals the destination multicast address. All that is done by this line over here, where you say proto tree add text, and we add it to the existing tree from the current buffer we say the offset of where we currently are plus 16 bytes. So that's the entire length of the NLRI. So we're covering the entire NLRI in one go. And this is the text that we use to describe that thing. And that's what I just went over. Okay. The problem with that is it basically gives you a line per NLRI. And it tells you what's going on. But in terms of being able to search the stuff or being able to break down into the individual fields, it isn't really showing you that level of detail. So if you went ahead and if you like clicked on the RD 904:82, it would just show you the entire span of those 16 bytes highlighted. You wouldn't really know which part is the RD and all that stuff. So that's the next part we're going to go add. Okay. So what we need to do is basically create a new subtree to attach to that blob of text that we created. So we use the function proto-item add subtree, and we create a child off of that existing tree, and that's what's being done over here. And we call this new tree prefix underscore tree. And yeah, okay. So the first thing to add is the actual the prefix length of the NLRI. This is pretty much hard-coded to 128 bits, but we're just going to grab it and paste it whatever the value is in there anyways. We shouldn't have gotten this far anyways, unless it was 128 bits, but we'll grab and put it in there. So what we do is we do proto tree add text and to our new tree, which is the prefix tree, and we say we go to the start offset, which is where the beginning of that NLRI is, and we go 1 byte deep in, and whatever that value is over there, we'll just say prefix length is the P line, which is what we grabbed earlier in the code. Okay. The next thing after that is the route distinguisher. So that's basically going to be another free text item. And what we do in that case is we do another proto add text. We do the TVB. We do the offset this time instead of the start offset, which is 1 byte further in. And this is 8 bytes deep. So we do offset length 8. And then we use our RD string and we fill in the route distinguisher with it, and then the text route distinguisher. Okay. Okay. So the last two ones are the IPv4 source and the IPv4 multicast destination. The way that we do that, we actually use the HF fields that we talked about earlier. And what I've done over here in the bottom, you'll see that you have HF BGP MDT default and HF BGP MDT source. So these are the new field types that are created. And one is called default MDT, the other one's called MDT source. Then we have the search text for it, which is bgp.mdt underscore default. And then I define what type of field it is. So it's going to be a field type IPv4. And the base is none, it doesn't really matter. And I forget what this was, actually. So there's no value. This is where the value mapping thing comes in, and the table mapping stuff. So there's nothing to put in there. There's no bit mask. There's no description really for it, and then that's the end of the thing. So once you define the field, you basically, in the proto tree item, you say you're going to add it to the prefix tree. It's going to be using this field descriptor, which is HF BGP MDT source. That's the buffer you're using, TVB. And you're going to be starting at offset plus 8. So 8, remember, was the route distinguisher. So you're going to go 8 past the route distinguisher. That's where the IPv4 source starts, and it's a length of 4, and that will add that one item to the tree. And you do the same thing with the MDT default. And what it looks like in the end is like this. So you have the NLRI. You have that one big blob of text that we created, right? Then we attached our subtree to it, and this is the length that we added, the 128 bits. Then we added the route distinguisher, the MDT source, which is from that HF field. And notice that it has, I mean, it created this all by itself. So all we said was basically that it was MDT source, and it added the IPv4 address, and then in the parentheses the IPv4 address, which would be translated into like a DNS host name or something like that. Same thing with the multicast. And you'll notice that there's trees created for the further MDT SAFIs that are there. The other thing that's done at the same time is that, remember these two guys that we created, the the bgp.mdt underscore default and the bgp.mdt underscore source, those are now available in the search text. So you can search for packets that are actually being sent for a particular default MDT or being sent from a particular multicast source. Okay. And here's an example where I'm actually looking for packets that are being sent with a BGP MDT default of 239.232.094, and actually filters out it throws away all the other packets and just shows me that update. Okay. After you have your set of change sets done, there's a nice utility that comes with a source called fuzz tests. And basically what this does is it basically looks at your existing capture files and it just plays around with them. It randomizes them. It tries to figure out whether you've got your decodes working with your pristine file. What if there were some changes with it? Does your code break in those cases? So what it does is you point it to, you've got your compiled Wireshark already. What you do is you point it to a capture file that you like, that you think is good, and what it'll do is it'll go through and it'll just randomize portions of that packet file and it'll compare it against, see if T-Shark complains about anything. If it does, it'll stop. Otherwise, it'll just keep on going forever. You can set it to go for like 100 times, 200 times, whatever. Okay? Once you're satisfied that your patch is good, you can submit it to the Wireshark website using the bug tool, or you can email it directly to the Wireshark development alias. What I actually do is I send it to the alias. That way, at least they can provide some commentary that you did something right, you did something wrong. They might pat you on the back. It's a little bit more better in terms of getting some sort of feedback for your stuff. In fact, for this particular patch, I actually had a typo in there, and somebody caught that, and they said, you need to go ahead and fix this. So I created a new patch and sent that out. So with the bug, it might actually take them a longer time to get to it. Okay. What you need to do when you send out the email is obviously attach your stuff. If you still have access to your capture file and it doesn't contain any sensitive information, send that along as well, because they'll add it to their build farm for what they use for sending out to for the mass builds, and they'll use fuzz tests on those capture files as well. Okay. For additional help, obviously you can email me, but the best place is the Wireshark developers list, and there's a really good archive on the Gmain website. So in summary, Wireshark, free open source network protocol analyzer. It has become the de facto network protocol analyzer today. I mean, within my company, we use it all the time. We have engineers that when we're testing new protocols, we build stuff out for it. There's some stuff that we don't publicize out into the open. There's some stuff we keep to ourselves, but in general, it's basically the de facto tool for this type of stuff. If you wanted to keep stuff to yourself, there's an entire architecture for doing plugins. So you can have a compiled version of Wireshark. You just put a plugin. You just throw your plugin into the plugin directory, and you have that additional capability. Okay. There's a CLI as well as a graphical display. I didn't really go into the CLI. The graphical display actually makes for better presentation material, but it is in some ways more featured than the graphical one because you can put in more stuff. There's hundreds of protocols supported. There's more being added every week, every month. Okay, and the one thing I basically wanted to leave you guys with, that it is extremely easy to add new protocols, and the Wireshark development people are actually very nice, unlike some of the other mailing lists, or the open source mailing lists, where they'll get on your case about anything. But they're very nice people to help you along the way, and that's it for me. If you have any questions, please.
Just now, I went to wireshark.org/security and found that in the last 11 months, there have been 4 different security advisories which boil down to the following protocol, application-specific analyzer can cause the following security issues. The fact that it can decode hundreds of different protocols in many ways is a security disadvantage. So just as a caveat, don't decode things that you don't really need to decode. Yeah, it's relatively straightforward to capture the bytes for a packet, look at it later if you need it. But doing random decoding of stuff that you don't need exposes you to considerable risk with
Absolutely.
Wireshark in particular, or any of these things in general.
Absolutely.
So you mentioned Jay Moran, AOL. You mentioned there was a plugins directory. As far as the plugins go, are there example dissectors already out there that you can kind of cut and paste? So
Yes.
instead of having to do the whole compile and everything?
Yep, so the question was, how do we get started with the plugins dissectors? In fact, the plugins are exactly the same as the existing dissectors. They just, in the beginning of the file, they just say something special in terms of this is a plugin. Don't build this out with the rest of the code. In the developers, in the Wireshark doc directory, in the readme.developer file, there's actually a cookie cutter sheet for the plugins themselves. So you can just copy that sheet over and just fill in the stuff that's different for your plugin.
Okay, so the plugins don't have to be compiled as part of the entire package. You can compile them standalone.
Exactly,
And
yeah.
then just add them in.
Yep,
with
exactly.
something similar.
In fact, they're supposed to be consistent across releases.
Okay, cool. And all the header files and everything for the plugins are available? Okay.
Other stuff? Okay, great, thank you.